What is magnet? So you are aware that magnet having a two pole, north and south pole, whether our earth is also going to behave like a magnet. And here we are going to see that magnetic effect of electric current. So how electric current is going to generate the like what we are getting due to magnet, how electric current surrounding of it is going to generate the properties of the magnet, or whether it will have similar kind when we will change the direction of the current, whether we have magnetic deflection will be same, whether magnetic needles are going to deflect in the same way. And apart from this, we'll see that how we are going to find the direction of the magnetic lines of force, as well as if you see that later, we'll see that how we are going to utilize this magnetism in the medicine. So finally, let's begin with our chapter. Okay. So its name is magnetic effect of electric current. So under this, we are going to see electric current and circuit. So already you know that electric current is the rate of flow of the charge, is the current. Again, we'll see that how magnetic field and field lines are going to work, how will be the movement. Then we'll see the magnetic field due to current carry conductors. Again, we'll see that if current carrying conductor is the straight wire, and how we'll find the direction of the magnetic fields or magnetic field lines. For that, we are going to use the right hand thumb rules. Again, we'll see that if current is going to flow through the circular loop, then how we have magnetic field. Again, we have another thing we call as the solenoids. So first we'll see what is the solenoids and how it's going to make the effect of magnet. Again, we have force on current carrying conductors. Okay, so earlier we have seen how due to the current magnet is being affected. Next, we are going to see how due to magnet, how current carrying conductor is being affected and its applications in the medicine, like we have MRI, that is called as magnetic resonance imaging that is used for the diagnosis. Then we'll see that domestic electric circuits, like in the house wiring, how we have different connections from the connection from the transformer to the home, how we have different colors of the wires. So let's begin one by one. So I welcome you all in this lecture. Okay. So it is about now electric current and circuit. So already we know that electric current. What is the electric current? I equal to Q by T. So that is the rate of flow of the charge per unit time. So now here, and already we have seen previously we have seen in electricity definition of the circuit. So what is the circuit? Circuit is the closed path. Okay. Closed path through which current is going to flow. Okay. So now here if you see that we have components of the circuits, like here we have resistor with resistance R, and here emitter, and this is the battery. So battery we are representing with the help of positive and negative terminal. So it is combination of the cell. And here we have switch key that is in the closed position since dot is inside this. And finally we have XY through which current is going to flow. So now here for this activity, if you'll observe here, so this some cardboard or some hard paper is taken around this, okay, through which this wire is going to cross. On that surface, magnetic needle is kept. So now when current is going to flow, so here what we are seeing that deflection occurs in the magnetic needle. So that magnetic needle having pole that we call as the north pole and the south pole. Okay, so that deflection takes place here. Again, if you change the direction, suppose now deflection is in the right side, and if you change the direction of the current, then deflection will be in the left side. So if the direction of the current is going to change, then direction of the deflection also going to change. So if current is going to flow here in this situation, okay, if current is going to flow here in the upward side, okay, and deflection is towards the left side, again if going to current is going to flow in the downward side, then deflection in the right side of the magnetic needle. So this one is observed by the Hans Christian Ørsted. Okay, he shows that electricity and magnetism both are related phenomena. So that discussion is done on the basis of this activity. So here, why already you know that same polarity having repulsion, opposite having attraction. So why magnetic needle is being deflected here? So this deflection shows that this current carrying conductor going to generate the magnetic field around that conducting wire. Okay, so that's why same repulsion, opposite attraction. So here another magnetic field is there apart from the needle. That's why deflection in the magnetic needle takes place. Okay, so from here we conclude that electric carrying wire behaves like a magnet. Now here we are going to see in detail magnetic field and field lines. So for this, if you see that again, we have discussion about the magnetic compass. So magnetic compass is the needle having a small bar magnet. So now, so that needle having two poles. One is called as the north pole, or that pole seeking toward the north. Okay. So it ain't pointing towards the north. Another pole is the south pole or south seeking. So this end pointing towards the south. So when we'll hang the magnetic needle, it will be in the direction of north and south. So now here in this activity, if you see that here in this case, that some iron fillings are kept here on the some cardboard. And finally, here if you are going to bring this bar magnet, or first of all itself you can keep the bar magnet here, and around this you are going to bring the iron fillings. So finally what you see that this iron fillings are going to arrange in particular structures. Okay, so that you can observe in this diagram, as well as in the below diagram what we are observing that magnetic field, magnetic lines is going to emerge from the north pole. Okay, it is emerging from the north pole and it is coming towards the south pole. So from one end it is going to emerge, and from another end it is going to meet here. So it is emerging from the north pole and it is going to merge at the south pole. Whereas if you see inside the bar magnet, the direction will be here from the south to north. Outside we are seeing from the north to south. Inside it is going to move from the south to north. And when we'll move away from the pole, so this circle dimension is going to increase. Okay, so that's why these magnetic lines of force are not going to intersect anywhere. So two magnetic lines of force will not intersect each other anywhere. So what is the, so here we have properties that like poles repel and unlike poles going to attract each other. When two north pole will be in contact, it will repel. North-south is going to attract. So again, we have what is the magnetic field. So the region surrounding a magnet in which force of the magnet can be detected. That is called as the magnetic field. Now this iron fillings is going to align in the direction of the magnetic field. So it shows that direction of how flow of magnetic field lines takes place. And magnetic field has direction as well as magnitude both. So now direction, How we'll find the direction of the magnetic field? Later we'll discuss about the left hand thumb rule. But here by experiment, by activity, you can observe that the direction is in which north pole of the compass needle move. In which direction north pole of the compass move, that is the direction of the magnetic field. And magnetic field lines are the closed curve. So it is going to emerge from the north pole and it is going to merge at the south pole. But inside the magnet, its direction is what, from the south to north. So that difference we'll see in case of solenoid, how it is going to be different inside the solenoids. And the strength of the magnetic field is the shows the closeness of the field lines. If field lines are more close, that means in this way here, if you observe that this magnetic field strength will be more in compared to this region. Okay, here we have less strength of the magnetic field and will close to the north or south pole. Here closeness of the lines are more, so its strength of the magnetic field is more here. Next, we are saying that magnetic field due to current carrying conductors. Okay, what we have seen little bit in the starting. So that we are seeing we are going to see here little bit in more detail. Okay. So we are going to see that this current carrying wire, this conductor, how it's going to generate the magnetism around them. Okay. So for that reference, if you see that here, this wire is taken here. Okay. And here direction of the current in the initial stage, if you see that in the clockwise. So finally, here you can observe that needle is also deflected here in the right side. Okay, so that you can observe here. This direction is the north, this is the east. So we can say that magnet is deflected towards the east side when direction of the electric current is what here? Clockwise. Okay, it is moving from left to right. Whereas if you see in the another circuit here, direction of the current has changed. Now it is moving in the anti-clockwise. Okay. So now here what you are seeing that in which direction magnet is going to deflect. So now it is deflecting in the west direction. So from this you are going to observe if direction of the current has changed, then deflection of the magnetic needle is also going to change. So this is due to the magnetic field around the current carrying conductors. Since like poles repel and like pole attract each other. Okay. So that is the observation from this activity. So if direction of the current has reversed, magnetic deflection also reversed. Now here we are going to see that magnetic field due to current through a straight conductor. So this conductor XY here is taken as the straight conductor. Through this current is going to flow. In that situation, we are going to observe about this magnetic field. Okay. So now again, if you see that in this situation, here we have variable resistance that is used to adjust the current that we are going to see in the ammeter, and in the series always current will be equal. That's why ammeter is connected in the series. So now in this you are seeing that if you are going to observe that current is going to flow here from the anti-clockwise, and here two reference point is taken here. One is the point P, another is point Q. So in the initial stage, that magnetic needle is kept at the point P. So here deflection will be observed. And finally here, if you see that later we have left hand thumb rule. So that thumb will keep in the direction of the current. And when we are going to wrap our fingers, so that direction in which we are going to wrap our fingers, that is going to give the direction of the magnetic field. So here, this thumb will be pointed in direction, and when we wrap our fingers, so it is moving here in the clockwise. Okay, so like that, how it is going to fold. So this is the direction of the magnetic field, which is shown here in the clockwise. And when we are moving away from the current carrying conductors, so finally that strength is going to decrease. So now if this magnetic needle will be kept at the point P, it will from P to Q, then deflection will be less. So from this, what we are going to observe that deflection of the magnetic needle shows that direction of the magnetic field. In which direction? Already we have seen earlier also, in which direction the north of the magnetic needle is going to align. It shows the direction of the magnetic field. Now, if you are going to change direction of the current flow, then direction of the deflection also going to change. And the current is increased, then deflection is also going to increase. So here we can observe by the ammeter readings. So by changing the resistance value, if you decrease the resistance value, current flow will be more. So finally you will observe that deflection is also more. If resistance value is more, then current flow will be less. Then we'll observe that there is the less deflection. So that deflection is going to depend upon the current value. So if current is more, deflection is going to increase. That shows that magnetic field strength is also going to increase. And magnetic field produced is going to decrease if you move away from the wire. So distance from the wire is going to increase. So finally, strength is going to decrease. So and here you see that concentric circle that is also going to change. When we are moving away, that radius or the size of this concentric circle is also going to change. So now we have another topic called as the right hand thumb rule. So what we are discussing earlier, with the help of right hand thumb rule, we are able to find the direction of the magnetic field. So our thumb should be pointed towards the direction of the current. In which direction current is going to flow through the conductor, in that direction we'll keep our thumb. After that, we are going to wrap our fingers. So the direction of the wrapping of the fingers shows that in which direction current is going to flow. So here we have right hand thumb rule. Okay. Left hand thumb rule. Later if you see that about the electricity in detail. So we have right hand Fleming rule, left hand Fleming rules, and we have right hand thumb rule and left hand thumb rules. So here right hand thumb rule is applicable to find the magnetic field lines. So by mistake, if I have told you somewhere left hand, so I'm sorry for that. Here only we are concentrating on the right hand thumb rule. So here if you see that right hand thumb is pointing downwards and we are going to wrap our fingers. So that in which direction we are going to wrap our fingers. So that shows that direction of the magnetic field. Okay. So that is happening here. So thumb points toward the direction of the current and finger wrap in the direction of the field lines of the magnetic field. So this was the right hand thumb rule. Okay. So that right hand thumb rule, thumb is in the direction of the current and the wrapping of the fingers shows that direction of the magnetic field. So here diagram may be looking less appropriate, okay, but you can realize by folding your fingers direction by right hand, okay. So now we have another thing is the magnetic field due to current through a circular loop. So now earlier we have seen that wire was straight. Now this wire become in the circular loop. So here X shows that this current is going to enter inside this coil, okay, and this I shows the current is coming out from that as per the direction. So now here, if you see that here, if you are going to again, if you are going to hold this wire in that thumb should be in the direction of this current. So finally, that wrapping of the finger will show that direction of the magnetic fields. On the basis of that, these arrows are drawn here. And when we are close to this current carrying coil, so finally you'll see that here size of this circle is small, but when we are moving away from the coil, that size of this ring is going to increase. Similarly here, in both end, similar situation is there. But when we'll see that when we'll move away from the both sides, so somewhere we are coming in the center of this coil, so this circle will become too much big, so that here this arc, that curved path will look like a straight line. So due to all these components of this current here, it's going to produce that the circle, whatever magnetic field we are going to observe here in the center of the coil, it will look like a straight wire, a straight line, not wire, a straight line. Now here, if you see that we have another setups. So in this, if you have current is going to flow through this coil, so again direction of this magnetic field is shown here. Okay, so now again right hand thumb rule you can apply here. On the basis of that, again we can see the direction of the magnetic field. So here at point A it is in this direction, at point B again it is coming in this direction. Okay, so here supply is given, this is the key. So if we have n number of the coil here, so that due to that field will be added. Okay, so finally field strength is going to increase if number of the turns are more, and all turns are going to carry the same current. So finally again if you'll observe that magnetic field produces inversely of the distance from the current carrying conductors. If you move away, magnetic field is going to decrease, and concentric circle size is going to become larger when we move away from the wire. At the center of the loop, the arc of the big circle appear as the straight line, and direction of the field can be obtained by again right hand thumb rule, or another is called as Maxwell corkscrew rule. Now suppose for example, in the direction of the flow of current, okay, already you know have about some idea about the screw. So on that screw some thread is there. So you're trying to move that screw in the direction of the current. So how will rotate that screw so that it will penetrate inside? So that will show the direction of this magnetic field. Okay. So like that you can observe. So that is also called as Maxwell's corkscrew rule. Then magnetic field directly depends on the current passing through it. So just now we have seen earlier also, if you have current is more, strength will be more. And if you have n turns of the coil, then field due to each turn will be added together. So that field strength is going to increase. Next, we are seeing here magnetic field due to current in the solenoid. So first we need to see what is the solenoid, okay? So here if you see that in this diagram, this structure is the solenoid in which many circular turns are there, and that is turns are wrapped in the to form the cylindrical shape, and all these magnetic that coppers are insulated. So two copper turns will touch each other, means it's not be like a short circuits. So they're having some coating, due to that it is insulated. Same thing happening in case of coil of motors, generator, or our fan, ceiling fan. Everywhere, wherever motor is there, one copper wire is passing over each other, but they are insulated layer is on that, so that's why it's not getting the short circuit. So now here in the solenoid, again if you see that supply is given, and this is the key. So again direction in the solenoid is similar to the magnet outside. It is coming from the north, emerging from the north, and finally is going to merge at the south. So these two end of the solenoid act as the north pole and south pole like this. But inside the solenoid, what you're seeing that direction is again all lines are inside are the parallel. Okay, lines are parallel. It's not going to like emerging and merging completely. Inside the solenoids, these lines are parallel from each other. So these parallel lines inside the solenoid shows that field is uniform. Okay, inside that solenoid also we have uniform field. And this solenoid is also used to make the magnet. So some soft iron is kept inside this solenoid, and finally if current is going to pass through this, it will magnetize the soft iron. So finally, what is the solenoid? It is the coil of the many circular turns, insulated copper wire wrapped closely in the shape of cylinder. So one end of this solenoid is going to behave as the north pole, another end is going to behave as the south pole. The field line inside that solenoid is parallel. So due to this parallel, what it shows that field is same at each point inside the solenoid. It shows that field is uniform. Now, what is the electromagnet? So just now we are discussing that the magnet can be formed due to a strong magnetic field inside the solenoid by magnetizing the material. So if some soft iron, some steel rod is placed inside the solenoid, and here if supply will be given, so due to magnetize this material having properties to get magnetized, and a strong electric magnetic field will be produced, then this electron, a strong magnetic field is produced due to what? Due to electric current. Okay, in through that coil current is going to pass. So finally surrounding of this we have a strong magnetic field, and finally this magnetic material, it is being converted into the magnet. This is called as the electromagnet. So this due to electric current, it is converted into magnet. So electric current, how we are getting? Due to flow of electrons. So that's why name is given electromagnet. Next, here we are going to see that force on current carrying conductor in magnetic field. So far we have seen due to current carrying conductor, how it is going to generate the magnetic field surrounding of that wire. But now here we are going to see that if you have a strong magnetic field, then how this current carrying wire will be affected. How much force this current carrying wire is going to feel. Earlier we have deflection in the magnetic needle. Now we are going to see the deflection in the current carrying wire. Okay. So here if you see that in this condition here, A and B point, if you try to observe here, and here a strong magnet is taken, so it has north pole here, this is the south pole. So now if current is going to flow in this direction, how connection is given here, okay, in the anti-clockwise. So here you are seeing that this point A is being deflected towards the left. Okay, so that means force is being experienced by this current carrying conductor, that is the AB. So this direction, how we'll find the direction? Earlier we have right hand thumb rule. Okay, so where we are trying to find the direction of magnetic field. Now here we are trying to find the direction of the field, motion, current, everything. If two compounds are known, third components we are able to find. So now here if you see that Fleming left hand rule, this thumb shows the direction of the motion, this finger shows the direction of the current, and this finger is going to show the direction of the field. So that thumb in the motion, this middle finger in the direction of the current, and this finally this will show the direction of the field. So like this, and always keep in mind, sometimes maybe direction of the flow of the current is not given. It will be given direction of the flow of the charge. So direction of the flow of the charge and direction of the flow of the conventional current both are opposite of each other. So if electron is moving, suppose from the top to bottom, then direction of the current will be from the bottom to top. So that middle finger should be as per the direction of current. That means it should be opposite to the direction of the flow of charge. So that we have to keep in mind. On the basis of that, we'll be able to find the direction of field, motion, current, if any two components are known. Third parameter we can find. So magnet also exert equal and opposite force on the current carrying element. So both are having equal capacity, can exert equal and opposite, and direction of the force on the conductors again depends on the direction of the current and direction of the magnetic field. Okay, so that motion, the force experienced by the conductor depend upon the field, depend upon the current. So this is the important thing here. Fleming's left hand rule to find the direction of motion, current, field. Right hand thumb rule was used to find the direction of the field, magnetic field. Next we have magnetism in medicine. So how this magnetic properties, what is happening inside human body, how it is can be utilized for the medicine, especially medicine means here in case of diagnosis. So an electric current always produce a magnetic field that we have seen from a starting onwards. Even if you have weak ion currents that travel along our nerve cell that also produce the magnetic field, but maybe that magnetic field will be weak, doesn't have much strength. But we have heart and brain that produce the significant amount of magnetic field. So that is being used for the magnetic resonance imaging. So it is the nowadays if you see that here in case of MRI we have electromagnetic waves. So that's resonance already know about this. Okay, when frequency is going to match, resonance is going to occur. So that image obtained by the MRI is helpful for the medical diagnosis, like any hair crack, any small fractures, any small tumor, all these things we are able to do. So this is advanced version of the CT scan. Next, we have domestic electric circuits. So in the house, we have so many wirings, but we are not much aware how it is going to work, am I right? So that we are going to see here in this case. So whenever if you see that in our home or in the factory, whenever we have connections, so minimum two wires, if you are going to take the single phase, so we have one live wire. That live wire color is what? Red. If you are going to take three phase connections, then three live wire will come. Okay. And another wire, if your here connection is whatever is shown, that is for the single phase. Another wire is the neutral wire. So generally, live wire is represented by the red color and neutral wire is represented by the black color. So the live wire is also called as the positive, black wire is called as the negative. And it has how we are going to recognize means this red color is the insulation color. Black is also insulation color. Inside what we have copper wire is there. And the potential difference between this live wire and neutral wire is 220 volt in our Indian system. And after taking the connection, what you are seeing that it is going to pass through the electricity board having fuse. So already we have seen in case of electricity, what is the purpose of fuse? When we have more amount of current is going to pass through this or when load is going to increase. So finally, fuse is made up of very thin wire that is going to burn. Okay. Finally, this wire is going to melt so that remaining devices, remaining circuit will be protected. So now when we are taking the supplies, so in the house we have energy meters. So how this calculation of the energy meter takes place, that also we have seen in the chapter of electricity that you can watch there. So that is the basis of 1 kilowatt hour. Okay, 1 kilowatt hour that we call 1 kWh. So that calculation also we have seen there. So now how much unit we are going to utilize in the home that will be deflected in the energy meter or electric meters. On the basis of that nowadays this also become digital, prepaid and postpaid. Like this depend upon city to city. After that it is coming to the main distribution box. Again this main distribution box having some main switch and fuses for each circuit. Okay, and some nowadays if you see that here we call something called as the circuit breaker. So that is the if any short circuit is going to occur, that is going to trip. So finally, our devices will be protected, our entire room connection will be protected. And here, this shows the socket connections. So now here, if you see that in this, when we have connection in the house, so it's like suppose we have refrigerator, geysers, AC, so they consume the high power. So for that purpose, 15 ampere wires are used, so that is for the high power. And for the normal usage, we have 5 amperes wires, so that is for the bulb, fans, all these things. Apart from this, what we are seeing, that third one is the green color. So that green color insulation shows that it is the earth wire, and it is connected to the metal plate that is pointed deep inside the earth for the safety purpose. So any leakage current, any ED currents are available, that is going to pass through this to the ground. So finally, whatever devices we are using in the home, so that metallic body is connected to this earthing to provide the load resistance path. So it is able to save us from the electric shock that is going to occur due to leakage of the current. So sometimes how short circuit going to occurs in the home. So when live wire and this neutral wire both are come in close, when insulation is not going to work, or by mistake due to wrong connections after pulling or something, one live wire and neutral both are going to come in contact due to short circuit which is going to occur. And another reason is the overloading. So overloading means more than capacity, more devices are connected to the same circuit points or to the same socket. That is called as the condition of the overloading. So these are the discussion where we have seen that how current carrying wire or current is going to produce the magnetic field, and how strength is going to change by increasing the current, how direction of the current will be changed, and how magnetic deflection is going to change. Again, we have seen that if you have a strong magnetic field, then how current carrying wire is going to feel the force. And to find the direction of the magnetic field, we are using the right hand thumb rule. And to find the direction of the motion, field, and current, we are using the left hand Fleming rule. Okay, these are the points we need to remember. And here we have connection for the domestic electric circuit. So any doubt is there, you write in the comment. Okay, I'll answer those questions. So it is very important for the examination point of view where you can then do the quick revision. Thank you very much.